Hi, everybody. Here we are today. We're doing section 1.5. This is going to be a pretty short video because 1.5 is pretty short. However, it's extremely important. 1.5 is very important. It's the fundamental theorem of Euclid. Sometimes we call this a division theorem, as you'll see. But basically says that if A and B are any two positive integers, there exist integers Q and R. Now, it's not a Q. Q reminds you of the word quotient. R reminds you of the word remainder. That's not a coincidence. Q is greater than or equal to 0, and R is also greater than or equal to 0, but less than B, which makes sense because basically what's happening here is kind of like taking A and dividing it by B. So I get a remainder, which is less than B. This is really what's happening here. With all the fanciness here, this is really dividing. So this basically says, so let's look at a simple example. Let's just look at a very simple example of this. Very simple example. Let's pull up a super simple example. And here we go. Let's pull my. So here we go. Okay. So if I have 17, divided by 4, I don't know. Let's say I have 17 and 4. Those are my numbers. So I'm saying that 17 equals, let's say, 4 times 4 plus 1. So this is my quotient. So my Q equals 4 in this example, and R equals 1 in this example. Ta-da! Let's do another one. Let's say actually I want to keep this consistent with the way the let's see, 17 quotient. Okay. So let's say we have, for example, 30 and 7. So 30 is equal to, let's see, 4 times, well, my quotients are always 4. Let's make it a little bigger. 30, 40, how about 40, 40 is, okay, let's do 40. So 40 is equal to, let's see, 5 times 7. So QR, which Q times B, so Q times, so that's 5 times 7 plus 5. Wow, it always keeps on being the same number. I don't want that. It's causing me sadness. I'm gonna make it 41. I want to have different numbers. Yeah, I want every number to be a different thing, so there's less confusion. All right, so in this example, A equaled 41, and B was equal to 7, and Q was equal to 5, and R was equal to, now it's going to be 6. Uh, 35 plus it, right. So in the example, if I have A and B are 41 and 7, so 41 is equal to 5 times 7 plus 6. Notice that 6 is, notice that 6, notice, let me put it here. Notice that 6 is less than 7, and it's greater than 0. Although 6 could equal 0, so I don't know how to do greater than or equal. 6 could equal 0, that's okay. Let's look at how it has it here. See if you notice, it says that R is greater than or equal to 0. So I'll have to put a little equal sign there somehow. How do we do that? Hopefully you'll know what I mean there. So that means 0 is less than or equal to R, which is 6, which is less than 7. That's what we're trying to say here. So I just want to show you how this actually works out with actual real numbers. All right, let's go back to the theorem. So if A is a multiple of B, the theorem is satisfied because A is just equal to QB and R is just 0. That's, duh. Now, if A is not a multiple of B, then A has to lie between two consecutive multiples of B. Notice if I would take all the list out all the multiples of B, 2B, 3B, 4B, 5B, 6, A would have to lie. So for example, let's go back to the numbers here. So in this case over here with 41 and 7. So I look at all the multiples of 7, 14, 21, 28. Eventually 41 is going to lie in between consecutive, 35, 42. Bingo, bingo. So notice that 41 lies in between these two consecutive, these two consecutive multiples of 7, 35 and 42. 41 lies in between. So that's what this is talking about. I'm just trying to take the theoretical stuff that they're giving you in the textbook and just give you an example of how it actually plays out. And let's see. So let's go back to the textbook. So we're going to call this, so A, which is in our case 41, is in between QB and Q plus 1B. In our case, it's in between 5B and 6B, 5 times 7 and 6 times 7. That's where 41 lies. Now, hence, there is an integer R, which is between 0 and B, and this is greater than 0 because now it's saying it's not a multiple. We're looking at the case where it's not a multiple, so it's saying R is strictly greater than 0. So there is a such that A is equal to QB plus R. There's if I take QB, I add some number R, which is less than B, I'm gonna get my A. That's all it's saying. And in case B is greater than A, then just Q equals 0 and R equals A, and that's it. It's a done deal. If so the proof of the theorem is complete. Now, what does that last line mean? If B is greater than A, what does it really mean by that? Suppose we had a case where suppose we had a case here where A is let's say A was 7 and B was 41. So what's going to happen is that Q is just going to equal 0 and R is just going to equal 7. So in other words, 7 equals 0 times 41 plus 7. That's all the last line is saying is that if B is bigger than A, then it's like a no-brainer. If usually we're talking about A is bigger than B, but either way it's going to work. And this is really kind of this is kind of what allows us to do division. Again, some of you may be thinking this stuff is, what's the point of this? So simple, so obvious. What are we wasting all this, spending all this time on something that's so obvious? Why are we doing this? Well, it's only obvious because you've been told these things, all your life. But imagine what we're doing here is imagine where there's no such thing as numbers. There's no such thing as anything. We're just creating a whole new system. We're creating the whole concept of numbers and dealing with numbers and all these different things. And we would have to prove all these things from this system that we're creating. We have to prove that these things work. That's really that's the best way I could say it. That's the best way I could say it. So that's why a lot of things we're going to spend a lot of time, not all of our class, but it will happen where we're going to be, proving things that are kind of obvious, but it's only obvious because you think it's obvious because you've heard it without really knowing why. So it just became obvious, what I'm saying. Anyways, we're also going to do and prove and do a bunch of stuff that's not so obvious, So we're gonna do quite a lot of good fun stuff in this class. Well, that is one, as I said, 1.5 is kind of a shorter section. As you can see, we're done. The next video, I'm sure some of you could guess, because I know you're brilliant mathematicians. So many of you, I'm sure, could guess that the next video is going to be 1.6. But for now, I bid you adieu and see you guys next time. Bye.